Hi everyone, this is Ankit from Mesh Cookies, and I'm here again with a brand new video on neural networks. This video is going to be an entry point for everyone who want to understand what a neural network is. So this video is going to be a two video series with ANN and CNN. In this video, I'll be talking about artificial neural network, and in the second video, I'll be talking about convolutional neural network. I'm going to go a little bit in deep of how this neural network works. A little math. Will be using hands-on code writing. I'll be doing a live coding in front of you to explain you how the neural network works. We'll be training a neural network to understand handwritten digits. Now, as you know, all the artificial neural networks, all the machine learning models require a huge amount of data in order for them to be trained. Luckily, we have a lot of people who have made a lot of things available to us already. Now, one of the dataset that we'll be using in this tutorial series is MNIST dataset. What is MNIST dataset? MNIST dataset is just a combination, a lot of images, which is a handwritten digits. Now, if you see the website, they have provided 60,000 images, which you could use to train your model, followed by 10,000 images, which you could use to test your models. All these images are well labeled. Now, in order to use this, we don't need to download the entire data set onto your system and then extract it of some sort. We can use Python to directly download all those training images in the memory, and then we can go ahead with it. Now, before we proceed, I will tell you two facts which will help you in the tutorial series. I will tell you a little about the Google Collab project that Google has provided to us, and second, a little about what images it will be giving us and what is our network. How does it look like? So let's get started. Now, this is a Google Colab UI, which is basically nothing but a Jupyter notebook, a fancy Jupyter notebook added with a lot of fancy things that Google has provided. Now, as you all know, GPU or TPUs are the best to train machine learning models. Why? Because they are very fast in doing iterative tasks on varieties of data. How do we get a GPU instance? I have a Mac, and it's really difficult for me to get a GPU instance. But lucky enough, Google's Colab will give me a runtime. If you go to runtime menu and click on change runtime type, you will see we have a GPU, we have a TPU version of the environment. I can use any one of them and start working on it. For now, we'll be using GPU. Now, as you can see, I have been assigned RAM, disk, and GPU for this particular session. This is basically an interactive Python session that I can use directly from the browser. I'll be able to write all the machine learning code right in the browser, download the entire thing right in the browser, and train it and predict everything inside the browser. So this is going to be a very good and handy tool for all those people who has resource issues, who don't have any GPU, because this GPU provides CUDA cores which will allow us to train our model real quick. So as you can see, I'm already up with the session. I can just start writing the code. But before writing the code, I would like to tell you a little about the image that we'll be using and the neural network. So you can see this image. Just try to assume this is a 28 cross 28 pixel image, which obviously it is not right now. It's just for reference that I have drawn these tables, but just try to consider that this is an image of 28 pixel by 28 pixel. This is a monochrome image. That means every pixel will have a value ranging from 0 to 255. Now, what happens when you train your neural network? Now, when we train our neural network, we give the pixel values, the entire pixel values to the neural network. Neural network try to start learning things, different patterns, edges, and whatnot. And this could be, this is basically a process of feature extraction where we extract all the feature of the image, or what are the curves, what are the edges that is required, that is there in the image. And then it will pass on to the new hidden layer or the next hidden layer, where you will understand a different part of it, where you will try to grasp, I mean the machine will try to grasp what a 6 looks like or what a 5 look like, and based on that will pass on to the next layer, where the output layer will be able to identify which image it is. Now, as you can see, there is a slight difference. I mean, I didn't mention anything about this in this big one-dimensional array. What is that? Now, for our ANN or artificial neural network, in order to get all the data or in order to feed those data, I just need to flatten this pixel here. So what I'm actually doing is I'm just taking this particular pixel and sending it here. Similarly, the next pixel, this is being sent here, and this last pixel will be sent here. So I'm doing nothing, I'm just taking those values and passing or creating a one-dimensional array so that I can feed it to our neural network. That is the main part of it. Now what we can do is we can now actually we're ready to write the code. So before we write the code, we need to make sure that we have TensorFlow 2 installed. Or if you don't have TensorFlow 2 installed, you can just install it using this command. This will directly, I mean, use equal to here. I mean, you just execute this command. This will download TensorFlow 2 in the VM which is assigned to you. It will install TensorFlow 2 right inside this VM. But I have already installed TensorFlow 2. I'll just verify if I have TensorFlow 2 or not. Now, if I execute this, it says 2.0.0. That means I have TensorFlow 2 already installed in my system. Next, I would also import matplotlib.pyplot, as this will be used to show images in the browser. When we download the MNIST database, we'll be able to see what images are there in the database. Now we are done with this. The first thing is we'll start downloading the dataset. In order to do this, let me just write this code and then I'll explain what is this. This is basically tuple. So this is the data structure that we'll be using throughout our training set. This is the training images, and this is the label of all those training images. This is the test images, and this is the label of all those test images. Now, in order to get the database, what we can do is we can download the entire zip file and upload it, and then do the memory mapping, or we can directly use this function dot datasets dot mnist dot load data. Now what this helper function do is it download the entire data set, and then it return and assign all those data to our data structure. So just let's execute this. It is going to download and set all those values. So it just downloaded. I mean, it was already cached, so it didn't take any time, but for you it will show you a UI where it is actually downloading the entire thing. Okay, just now let's just check what data we have. If you check the shape of this tuple, you can see we have 60,000 images, 60,000 handwritten images, which is basically of resolution 28 pixel by 28 pixel. This is what it is. Let's see what we have at the first index. So if I print this, you will see an array. Now this is basically the first image in the array, which is 28 pixel by 28 pixel. As I earlier told you that this is a monochrome image. That means every pixel will have value ranging from 0 to 255. So this is the entire array. This is the first image in the list. If we want to see this image, we can plot it. plt.im show. Now this will help us visualize what is there. So the first entry in the training set is the number 5. Forget about the color. This is basically not we have to use a binary variable, binary parameter in order to do that, but we'll skip that. It is good for our understanding that the first entry in the training image is, and the 60,000 images, the first image is the number 5. We can also see what is at the first index, which is 0. We can also see what is the second index, which is 4. So this contains similarly 60,000 image, and every image is 28 pixel by 28 pixel. So this is the training image, and let's also check what is there in the labels. So if I see y_train.shape, this should be 60,000. 60,000 as I expected, because this is basically an array of all the numbers that is there. So if this is 60,000 images, this is 60,000 labels. So as I have shown you, at the second index we have 4. So if I try to access second index, it should give us 4. As it is 4. So and we just verified that okay, the data are correct. Similarly, we can do verification for x test and y test, but that is not required right now. Let's just get rid of this. Now before we can write any neural model, any neural network, we need to pre-process the data a little bit. First pre-processing that we will do is we will divide all the pixel value by 255. By doing that, we'll make sure that all the pixel values are between 0 to 1. This will ease our process of training. So in order to do that, we'll just divide xtrain by 255, sorry, and x test by 255. By doing this, we just created all the pixels in the range of 0 to 1. Let's just verify this once. So as you can see, 0 0.9, 0 0.5, all the pixel values has been modified because we divided it with 255. So obviously we'll have pixel value ranging from 0 to 1, not lesser or more. So this is done. The second pre-processing thing that we need to do, as I have already explained in the image also, that we need to flatten this 2D matrix into one-dimensional matrix. In order to achieve this, we just need to reshape this NumPy array. As you know, this is basically a NumPy array. We just need to reshape it, and in order to achieve that, we just need to write x_train dot reshape. Now we are going to reshape 60,000 images to 784. Try to understand where the 784 came from. Let me just, now if we have 28 into 28, which is 784. Now what we're doing is, as I have already shown you, we are going to open this 2D matrix into one-dimensional array. That means we're going to create a 28 into 28 single dimensional array, which is total 784 pixels. So exactly what we're doing here, we are going to break the 60,000 array into 784 parts. That will give us total of 60,000 images, which has been converted into single dimensional matrix. So let's just execute this for x_train and x_test. Okay, So our test data set only contains 10,000 images, not 60,000 images. So this is done. Now if I show you train 0, you will see a single array. This is not a multi-dimensional array, this is a single array containing a single value, and those pixel value are only ranging from 0 to 1. Now we are ready with the data. These data are completely ready to be fed to our neural network. Now we can start writing our neural network. So let's just get rid of this. Now in order to create neural network, we need to write a model. Now in order to write a model, TensorFlow gives us a helper function. We will be using sequential. This is our model. Now as I've already shown you, we are going to create three layers inside it. First is the input layer, second is the hidden layer, and third is the output layer. So let's just add the first layer, tf dot chaos dot, the first layer that will add, which is basically a dense layer. Now this layer requires us to enter the units, which is basically 74. This is basically the output that will be coming from this layer, followed by a loss function, activation function. Activation function is basically responsible function who will be basically activating this neuron, how this neuron will be activated. There are a lot of activation function that we can use. We'll be using sigmoid for this. Now since this is the first layer of our model, we need to give it a shape, input shape. How many input will be provided to it? This is the first dense layer of our model. Now we'll write the hidden layer, which is of 128 unit. This hidden layer, we're creating 128 neurons inside this hidden layer. So model dot add f dot keras dot trans units equal to 128. As I said, we need to only specify the output, and we also need to specify input for just the first layer, because we need to tell how many inputs are coming into the first layer. Now for the activation function, we can use ReLU, and finally we'll add one more layer. This is going to be the output layer, and units equal to 10 with activation of softmax. Now in order to understand why I use which activation, you just need to understand and learn a little theory, how things work. But for the most part, the activation function is responsible for making sure which neuron will be activated when. And as I've already told you, that the first layer should be specified what is the input shape, because it needs to understand how many neurons it has to create. But this input shape means if we are giving 784 input, definitely there are going to be 784 output. Now this 784 output is going to be fed to 128 neurons, which is then the output of which is going to fed to 10 neurons, which will be giving our answer. Let's just execute. Okay, we need to use layers here. So basically all these dense function come inside the layers. I was actually assuming why I was not getting uh, the helper functions, but anyways, that was a small mistake. Now our model is ready. If you need to see we can summarize. Okay, this spelling mistake. Now, as you can see, this is basically a sequential model having 74 output from the first layer, 128 output from the second layer, and finally 10 output from the third layer. The total parameters that can be trained is 717210. This is basically the weights and biases, which is basically developed by creating the dense layer. Dense layer basically every layer of input is connected to every layer of output like this. For example, if you see all the inputs, so if you consider all these as 784 input, every input is going to every neuron of the second layer, similarly to this, and finally to this. So this is basically the model that we have right now. Now we have written the model, we need to compile our model. In order to compile that model, we need to provide the optimizer function. There are a lot of optimizer functions available. There is gradient descent, which is a classic one. Then we have stochastic gradient descent. Then we have Adam, and there are a lot of other optimizers that is available in the market. We can use Adam here. We need to define the loss function. There are a lot of loss function available in the market. Again, we can use cross entropy. We'll use sparse categorical cross entropy, and the matrix that will be training to should be accuracy. Let's just compile our model. Now, what happened when you actually train your model? Before the next step is basically training the model, but before training the model, I need to give you a little detail of how this training works. So when we give those 784 input to the first layer, then followed to the second layer and the third layer, there are random weights and biases that has been assigned to all the neurons. Now this weights and biases creates an output. Now, as I have already shown you that this images already came as a labeled image. So the output that is generated by our neural network can be compared to what should be the original output, and the loss, which is basically the difference between what it should produce and what the output has given. This there is the difference between them is the loss. This loss function has to be decreased using an optimizer. So what optimizer do? I mean, there is a process called backpropagation, where every weight and biases is recalculated in a back propagated way. Every so basically there is the differential is calculated in terms of how many loss is generated using the change in the weight. This is basically goes in chain to the first, and that's how the chain rule came. There is a multiple differentiation that happens throughout that neural network layer, and every change in the weight will result in a change in loss, and that is basically being decreased, or that is basically the entire idea of machine learning, where you just need to reduce the number of loss that you have. So this is how, on the crux of it, how neural network works. I'll create a separate video where I'll talk about the mathematics behind it, how the chain rule works, how do we differentiate, and how the backpropagation work in order to change the weights and biases. So let's just start training our data. So we need to provide data first, which is xtrain, and the label, which is ytrain, followed by a loss function. Okay, sorry, we need to provide epochs. Let's say we can give 10 epochs, and a batch size that should be 128. Now when I hit execute button, what is going to happen is uh, this fit function is going to take input in a batch size of 128, and is going to train the model one by one 10 times, and it's going to generate loss and accuracy. Let's see. So this is the first epoch. It is training on 60,000 images. It is the first epoch generated an error of loss of 0.4, followed by an accuracy of 0.877, which is pretty good. This is second epoch, third epoch. Similarly, we have total 10 epochs. The idea of this epoch is to decrease this loss. That's what I discussed when I was explaining neural network loss function. So as you can see, we are decreasing the loss. This is 0.2, this is 0.1, then 0.09. So the optimizer, the Adam optimizer, is basically working here to create, to decrease the loss and increase the accuracy. This is the last epoch, and you can see we achieved accuracy of around 98, which is pretty good, with loss of 0.0336, which is again very good compared to the loss that should be there. Now our model is completely trained and we are ready to predict if our model has been trained correctly or not. Now before we proceed, I'll tell you what the model, the function is model dot predict. Now we can either pass the entire input data set, or we can test it one by one also. So in order to test it, what we can do is we can pass zeros. So as you remember, the zeroth number was 5. We can also recheck it. Now once I press this predict button, this is going to give me an array of accurate percentage of 0 to 10. It will give you an array how much the model think that this particular image is 0 or 1 or 2 or 3. So if I press enter, you can see I got an array of 10 digits. Now this means that this is the amount by which the model think that it is 0. This is the amount by which the model think it is 1. This is the amount by which the model think it is 2. Similarly, this is 3, this is 4, this is 5. So you can see the array contains the highest value here. That means that model is saying that the image that we have passed is pretty much 0, 1, 2, 3, 4, 5. This is 5. Now in order to make sure that this is 5, what we'll do is we'll check the corresponding label. So if I press 0 here, it should output 5, which is absolutely correct. That means our model has been trained completely right. Let's just test it with other number. Let's say we pass 7th entry here, the 7th image, and the model prediction says that it is last value, which is 9. So if I try to access that, it should be 9. Oh sorry, this is 9.7. The highest is 9.9. So 0, 1, 2, 3. So it is basically 3. That was my mistake. It should be 3. So this is 3. So yeah, this is pretty much it. To summarize, we wrote an entire neural network. We trained the neural network on 60,000 images, and then we predicted the trained neural network in order to get the results, and the results are pretty much accurate. What are the use cases of such a model? This is just the entry point of machine learning, where you write the very normal neural network which is able to just predict a fixed image size. If you want to predict something else, it won't predict, because this has been hard coded to predict an image of 28 cross 28. So if you want to test this model with a new image, you need to create a image of 28 cross 28, convert that into a numpy array, and then pass it to this model, and you'll be able to test it. So in reality, this doesn't happen. You will be able to, pass any resolution image to your model, and you'll be able to train it. Normally, what happens is you collect a lot of data set. Suppose, for example, you want to test. You want to write a model which will be able to recognize maybe QR code. So you need to take a lot of images, and then you need to mark where the QR code is, and then you need to feed it to the system. The system then the model will then learn what QR code is, and then you'll be able to directly use it. So for now, you just need to save this model, and then you'll be able to use it for any purpose. Maybe for OCR, you can directly use it for. There are a lot of libraries that are already there in the OCR, but now you have a machine learning model written in couple of in 30-40 minutes. We just wrote that complete machine learning model that will be able to do the OCR. So that is the beauty of it. So that is it for the video for the most part. Comment or like or subscribe, ask questions if you have. I'll be recently, I've already started working on the next tutorial, which is convolutional neural network, where I will be talking about how to use images, how to use RGB images, how to use convolution to create different filters and different sides of the image and different feature extraction techniques, and then writing the neural network model to train this model and then test it. That second video is going to be again very a little techy, but for the most part, everybody who want to understand how neural network works on the crux of it, this video is going to give you a complete understanding of how a neural network works. In order to get a mathematical understanding of how neural network work, in terms of, for example, when I was learning it, I was very much keen to understand the mathematics behind it, and I learned everything. I read a lot of papers, I read a lot of research documents, and then I went to the documentation and the framework also, and then I understand a good idea. So comment in the comment section if you need to understand. Based on that, I will create a video telling how different things work, what is backpropagation, what is model overfitting and underfitting and stuff like that. So that should be it for the video, guys. Thank you so much. Bye bye.